This video is going to cover Chapter 5, Section 4, which is called Use Medians and Altitudes. So in this section, we're going to learn about two more segments, special segments that we're going to add to the mid-segment, perpendicular bisector, and angle bisectors. All will be covered on the test at the end of this chapter. So we start with the median of a triangle. And the median of a triangle is the segment whose endpoints are a vertex of the triangle and the midpoint of the opposite side. So this median connects the vertex to the midpoint of the opposite side of the triangle. In this triangle, triangle ABC, the median that's shown is CD because it starts at C, which is one of the vertices of the triangle, and it hits the opposite side at its midpoint, which we know because of the congruent marks. Every triangle has three medians, and the medians, like the perpendicular bisectors and angle bisectors, are concurrent. So if I were to draw a median from this angle, I would say it's about there. It goes from, again, vertex to midpoint, and then to go B to the midpoint, which I'm going to eyeball up, but I'm going to say it's about there. 1, 2, 3, 1, 2, 3. Notice that they all meet, and again, that's a point of concurrency. The centroid is the name of that point of concurrency. The point of concurrency of the medians of a triangle is called the centroid of the triangle. So far we have the circumcenter, which is the point of concurrency for perpendicular bisectors. We have the incenter, that's for angle bisectors, and now we have the centroid. So circumcenter is to perpendicular bisectors, and incenter to angle bisectors, and now centroid to medians. Like the incenter, the centroid is always inside the triangle. So it doesn't matter if that triangle is acute or right or obtuse, the centroid is always inside the triangle. The centroid is also called the center of gravity because this is the point where a triangular region would balance. So if you had a triangular shaped board or paper or anything like that, you could actually balance it off of a pole if you placed that point at the edge of the pole right there at the centroid. This would completely balance your triangle out. It would lie flat. The concurrency of medians of a triangle theorem, just like all the other special segments, this one has, again, a theorem, says that the medians of a triangle intersect at a point, that point's called your centroid, that is 2/3 the distance from each vertex to the midpoint of the opposite side. So they're not congruent like the other ones. This is a little bit trickier. What it says is that so if I look at B, F as my first, this is one of the medians. The length from B to P, which is from vertex to centroid, is 2/3 the length of the whole segment, which is BF, which means from P to F would be 1/3 the length of PF. If you look here on the left, it says AP, which is this part of that median, would be 2/3 the length of AE. BP is the one we just showed, and the last one would be CP is 2/3 the length of this whole median, which is CD. So when you look at a diagram, you should definitely be able to tell that there's a difference between the 2/3 and the 1/3. But if you get confused by this, remember that the 2/3 always goes from the vertex. So vertex to centroid is 2/3, and then centroid to midpoint, centroid to midpoint is the other 1/3. In example 1, it says, in triangle LMN, RL is 21. So this segment here is 21. And SQ, this segment here, is 4. It wants you to find LS and NQ. So the first thing that you want to look at is, because all of these triangles and different special segments are going to be put together, you want to identify that you're looking at a triangle in which all of these segments are going from vertex to midpoint, vertex to midpoint, vertex to midpoint. So because of that, you know that the point in the middle there is your centroid, and you have the 2/3 rule. So the 2/3 rule says that the whole segment, which is RL, would get divided into 3 parts. 1/3 of it is going to go to the smaller segment, like RS, and 2/3 of it is going to go to SL. So LS is going to equal 2/3 of 21. 3 goes into 21 7 times, and 2 times 7 is 14. So LS is 14. Then you want to look at NQ. So NQ falls along this median, and what we have is 4. So 4 is SQ, which is the 1/3 part. NQ would be 3 times that. So I would do 4 times 3, which is 12. If it had asked for NS, then I would have known to double 4, which is 8. And then again, I can always just add those 4 and 8 to get the whole length, which is 12. So vertex to centroid is 2/3. Centroid to midpoint is 1/3. Example 2 says a sculptor is shaping a triangle piece of iron that will balance on the point of a cone. At what coordinate will the triangular region balance? So remember, we're looking for the point of balance would be the centroid. And the way we find the centroid is by finding the midpoint of each side, drawing my median, and then finding the point where they all meet. So if you can identify your midpoint easily, like if it's vertical or horizontal, then you can go ahead and do that. But these are not that case. To find the midpoint of each side, I'm going to start with these two. I'm going to say 6 plus 10 over 2 and 6 plus 7 over 2. And I get 16 over 2, or 8, and 13 over 2, or 6.5. Then I'm going to go to 8 and 6, 2, 4, 6.5, which is that point right there. That's my midpoint. And then I want to draw a segment that connects the vertex to that midpoint. So that's one of my 3 medians. Now I'm going to find the midpoint on this side. So I'm going to do 10 plus 8 over 2. 7 plus 2 over 2. I get 18 over 2. 9 over 2. So 9 and then 4.5. I'm going to go 9, 1, 2, 3, 4.5. There's my midpoint right there. And now I'm going to connect that vertex to that midpoint. And then the last side that I'm going to find the midpoint of is here. So I'm going to do 6 plus 8 over 2. 6 plus 2 over 2. 14 over 2, which is 7. 8 over 2, which is 4. So now I'm going to go up 7, up 1, 2, 3, 4. There's my midpoint. I'm going to use my median to connect it, and then I can identify where these 3 points meet, which is going to be my centroid, and that's at 8, 1, 2, 3, 4, 5. So my centroid, or point of balance, is 8, 5. Center of balance. Okay, the next special segment that we're going to learn about is the altitude of a triangle. And the altitude of a triangle is a perpendicular segment that goes from the vertex to the line containing the opposite side. So what it has with the perpendicular bisector, what it has in common with that is the perpendicular, but the perpendicular bisector doesn't necessarily go to the vertex. It goes to the opposite side. So perpendicular and then midpoint would be perpendicular bisector. Altitude is going to be vertex and perpendicular. So these tend to be one of the hardest because, like everything else, every triangle has 3 altitudes. And like the perpendicular bisectors, they can be inside, outside, or on the triangle. And that's dependent on what kind of triangle it is. So if I had an acute triangle, let's say, which could look like this, and I'm going to zoom in on that so that we can draw. So for the altitudes, I'm going to start at the vertex. So if I start at this vertex here, I want to draw a line that is perpendicular to the opposite side, and that would be my altitude. And then what I'm going to do is going to rotate my triangle around, and I'm going to look at the other vertex, which is here, and I'm going to draw, again, a line so that it's perpendicular to the opposite side, which would be about there. And then I'm going to rotate it so that the third, line that up, so that the third vertex is at the top. And I'm going to draw the line that is perpendicular from the third vertex to the other side, which would be there. Now I'm going to rotate it all the way back around so that we can look at what we've drawn. Here we've got, obviously, this is an acute triangle. And on the acute triangle, we've got the 3 medians that meet inside the triangle. That one's honestly the easy one. Now, if I were to draw a right triangle, still not too hard. When I go to find the perpendicular segment that connects the other side from the top angle, you're going to see that that line is already the side of the triangle. So if I come from this top vertex here and I draw my perpendicular segment, it's actually going to come straight down because it's already the side of that triangle. Now if I rotate it, so that this vertex is now at the top. Again, I draw my line that goes straight down. And again, it's the side of the right triangle. Now the last side to draw comes from this vertex, and it would go straight down, being perpendicular with the other side, which would be about there. So now when you look at the right triangle, you should see, let's turn it all the way back around, that these 3 meet, or the point of concurrency is at the right angle. So this is on, this would be a right triangle, and it's on the triangle where they meet specifically at the right angle. Okay, so now the last one is your obtuse triangle. And if you pay attention to the wording on this definition, you'll see that it says that it's connecting the vertex to the opposite side or the line containing the opposite side. And this obtuse triangle is why that happens. So if I wanted to, let me start with the easy one. I'm going to rotate so that this one is at the top. So if I wanted to connect that vertex, which is here, to the opposite side, making it perpendicular, I just drop it straight down. Now when I rotate it so that this is at the top, now I want to connect from this point to the opposite side, but I want it to be a right angle. So if I take this line, no matter where it hits that blue line, it's not a right angle. It doesn't become a right angle until, if you could imagine, it comes all the way outside your triangle. which is why it says that it would need to be extended beyond your triangle. So the line containing this. So if I were to extend out this line, that's where the intersection would be perpendicular. And the same thing is going to happen on the other side. So if I rotate it around, this one's not completely connected, but it would have been. Let's say it's here. If I look at this vertex now and I want to connect it to the other side, it would have never happened inside this triangle. However, if I were to extend this line out, it would happen, maybe not exact, but around there, which means that my point of concurrency is happening sloppily, but it's happening outside my triangle. Let's see if we can get those to be a little bit straighter. So with a ruler, with a compass where you could measure the right angle, you'd be a little bit more accurate on all this stuff, which we're actually going to work on a little bit next week, the constructions of it. But basically, these three should eventually meet somewhere outside of your triangle. And that's where the in, on, out comes from. So in my obtuse triangle, which is super sloppy, they meet outside. So that's where your in, on, and outside come from. In is your acute, on is your right, and outside is the obtuse. And that special point, which, again, point of concurrency, has a name just like all the others, which is called the orthocenter. So in triangle QRS, altitude OY, this should be over here, is inside the triangle. Ignore this one. But RX and SZ are not. Notice that the lines containing the altitudes are concurrent at point P. This is the point of concurrency, which is the orthocenter of the triangle. So the diagram that's there, that's obviously a little bit neater than what we had drawn. This is an obtuse triangle. And if I had connected the altitudes of this triangle, which is all the red, you would see that they meet at a point that's outside, and that point is called the orthocenter. The good news about the altitudes is they're complicated in the beginning, but they don't have any theorem attached to them. There's no congruent length, there's no equidistant, there's no 2/3 rule. This is the only one that really all you need to know about the altitude is its definition, which goes from vertex to opposite side at a right angle, or the line containing that opposite side, and they meet in, on, and out. That's all the information you kind of need to know about the orthocenter. Example 3 says to find the orthocenter of triangle XYZ with vertices X, -2, 2, Y, 3, 6, and Z, 7, 1. So again, we've been talking about it, but at the end of this chapter, all of these terms are going to get blended in together. So it's important to identify that orthocenter means where the altitudes meet. So the first thing I'm going to do is plot these points. X is -2, 2. Y is 3, 6. And Z is 7, 1. And then I'll connect these points. So I know I need to find where each side connects to the opposite side at a right angle. What does look true about this triangle is that it looks like right here is a right angle. And if that's the case, then I know that the orthocenter is actually going to be at that point, because it would be where the sides meet of the non-hypotenuse sides meet of my right triangle. But in order to determine that, I have to be sure that the slope of xy is going to be the opposite reciprocal of the slope of yz. So first I'm going to find the slope of xy. So I'm going to use these two. y2 minus y1 over x2 minus x1. And I get 4/5. Then I want to find the slope of yz. So now I'm going to use these 2 points. And that would be 1 minus 6 over 7 minus 3. And I get negative 5/4. So I've confirmed that these two are opposite reciprocals of each other, that this is the right angle. And given that piece of information, I would know that the segment connecting this vertex to the line containing the opposite side at a right angle would be that side of my triangle. This vertex to the line containing the opposite side at a right angle would be that way. And this vertex at the top, perpendicular to the line on the other side, would be something like that. These would meet at this point of concurrency here, or orthocenter, which is 3, 6. So the orthocenter would be at 3, 6. You can use the remaining time to work on your homework assignment. So it is 11:8, H2, 5.4 homework. Available on Canvas, and then make sure you submit your notes to the assignment that's also on Canvas. That is 11:8 classwork to 5.4 notes. You need to do that before, so do it now because it has to be done before the end of the class. Have a great weekend, and I will see you Tuesday.